SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 4, that is Hydro and Renewable Energy Power Generation Systems. In today's lecture, we will focus on another category of renewable energy, that is geothermal energy. So, we will touch upon topics like origin of geothermal energy, different types of geothermal energy systems, and whatever most possible and effective way of harnessing this geothermal energy are of two types, and they are mainly on hydrothermal systems, and we call them as vapor dominated systems and liquid dominated systems. So, they are typically hydrothermal systems, and we will try to see why we say hydro, because it is mostly the working fluid is water. So, that is the reason we say it is a hydro, but however, this water is not in its purest form, it is highly saline. At the same time, there are many gaseous components which are already present in this water. So, that water content we call this as a brine. So, I will talk about those aspects in this lecture. Now, let us understand that where we are in, if you look at power generation systems through fossil fuel energy as a reference. So, in these fossil fuel based power generation systems, that is mostly steam power systems, our main focus was that energy that comes into these systems through boiler or steam generator is fossil fuel combustions or coal based combustions in presence of air. But with depletion of fossil fuels, we switch upon to other sources of renewable form of energy. They are geothermal, solar, nuclear, they are possible ways. Until this point of time, we have covered this passive form of solar energies which is available in nature, that is called wind energy, then ocean temperature energy conversion, OTEC plants. Then we have hydroelectric energy that comes by virtue of solar heating, and that which is available in the form of rains, creating a dam. We can store the energy of water, and that energy is the potential form of energy, and through this process we convert them to kinetic energy, and subsequent rotating the turbines we get harness the power. Then we have this tidal energy, which is mainly by virtue of the gravitational effects of lunar and solar cycles on the ocean surface. So, basically all these forms of energy which we have discussed so far, they are renewable form, because they all of them come from the solar energy and effect of solar energy on this surface itself. So, we will talk about the solar energy much later, but now let us dig into the fact that if at all whatever form of energy which are available on the surface, that is termed as renewable energy, but there are other possible ways that we can energy is also available in the earth's crust, and those are also renewable form of energy, and they comes under the category of geothermal energy. So, basically geothermal energy is also a kind of renewable energy, but it is available not on the surface or in the higher atmosphere, but it is underground. So, it is available in the earth's crust. So, we know that earth formation of earth has started in millions years of ago, and if you take this inside crust of earth, there are all the materials which is mainly, because earth crust is mainly made out of carbon materials, and they are available in plenty within the earth's crust. So, if you dig into the earth, we will find many sources of energy, the energy resources which are available in plenty, and they are nothing but your heat source. But if you can tap those heat source, then we can get a substantial amount of energy which is capable for running a power plant systems. So, what we can say that geothermal energy is a kind of a natural energy resources, and they were available since the formation of earth, but till this point of time our main attention was mainly high energy density contents, and those are in the form of fossil fuels. So, essentially all the fossil fuels are derived from the earth's crust, like all the petroleum products, they are derived from the earth's crust, and till this point of time there was no scarcity, but since there is a scarcity of these fossil fuels, because rate at which energy demands are coming, the fossil fuels are no longer is supposed to supply this, because although nature makes its own fossil fuel through its ecological processes, but what happens, the rate of demand is much higher, so it cannot supply. So, human attention is now more focused to other sources of natural energy which is again available in the earth's crust, but they may be in a lesser energy contents, and those energy contents are still unattended, because with our available technology so far we are not able to reach those energy resources. But now time has come that since the fossil fuels are depleting, we should also dig into those low energy contents which is available in the earth's crust. But what happens is that those are predominantly available in some localized pockets under the earth's surface. So, basically these low energy contents, they are not available in every places on the earth, they are available in specific locations on the earth's surface. So, essentially geothermal energy, if you look at, they are available at some locations where we used to see volcanoes, we used to see lavas. So, that means energy from Earth's crust tries to come up in the form of fire or high density gas that comes out from the Earth's crust through some passage or vents. So, if you can tap those kind of things, energies, then it becomes a better usage of our natural resources in the form of renewable energy. So, now let us see that what is this geothermal energy. Let us try to understand the origin of geothermal energy. So, what we can claim like this is that geothermal energy is the energy resources which is available in the form of heat, and this heat has to be transported from the interior earth through steam or hot water. That means, if this we can tap this in the form of hot water or steam, then we can harness this. So, it is also in the form of renewable, but they are not available in plenty at every locations of earth interior, but they are geographically they are available at some specific locations. But unfortunately, with our available technology, we have still not available conventional technology, we are not been able to extract that energy. But these natural heat energy, how do you say that that location is a geothermal site? We will find those locations there which are more prone for volcanoes, lava flows, hot springs, geysers. they like some hot spray of water that comes out from the underground. So, that is a location which can be treated as a geothermal energy resources. So, just to give some history of these resources, because earth is said to have been created by a mass of liquids and gases, out of which 5 to 10% are the steam. So, when this fluid is cooled down by losing heat on the surface, that means these steams, when they try to come out of the surface and they form, when they try to cool down a losing heat surface, the outer solid crust is formed with an average thickness of 32 kilometers. So, while these are the numbers, realistic numbers that has been taken from the book, and so what happens inside, there are some solid crust, they, when those energy they find some passage to come out, they come through certain vents or some passages, and through that passage when they come out, they try to cool down. When they cool down, they come as a condenses as water, and what water we see in the sea or oceans, they are nothing but that comes from the earth's crust, and that is what it is claimed. Now, if you actually dig into the earth crust, we have molten mass that is called magma, and these are still till now also these magmas are in the process of cooling, and so when they cool on the earth surface, they form seas or lakes and oceans. And another point that I would like to mention is that the historical background tells that many earth tremors, that means whenever there is some kind of a earthquake, so we will find some kind of disturbances in the different layers of earth surface. So, due to these disturbances in layer, there are some passage or cracks which starts developing inside this earth crust, and those are the kind of the passages that gets initiated for this formation of these volcanoes or lavas. Now, through this process what happens, whatever materials that are stored inside the earth, they try to come out. So, initially it starts with this magma. So, when the magma tries to come out through this, so we will have steam, we have brines, and when they come out by mixing with different parts of earth's crust. So, thereby many gases also are diffused within that component, and we entire things we call this as a brine. So, essentially when you dig into earth's surface, if you go much deeper, whatever liquid material that we are going to extract, that will be called as a brine, because it is a mixture of so many water plus so many other gas components. So, that is the main reality of these geothermal systems. Now, with geothermal point of view, these cracks or vents are called as fisheries. So, that is nothing but these are the passages through which the inside materials of earth tries to come out. Now, let us see the more pictorial representation of a typical geothermal field. So, we will try to see that what is the geothermal resources which are available. So, essentially speaking, this picture shows that one particular geothermal field at a given geographical locations. Now, in a geothermal field, and there are different zones. So, they are mentioned as A, B, C, D, E, F, G and H. So, what we see here is a much below this earth crust. So, we are going deep into this earth crust. So, we say it is a underground. Now, if you go much deeper, we will find a regions where we will find the zone A. So, zone A is known as hot magma zone. So, this hot magma zone is the main resources which where these things are available as a molten materials. So, they are like some kind of boiling materials which starts boiling inside the crust, but they tries to come out, but they are unable to come, because there are so many different layers through which it tries to come. So, when they tries to come, this molten mass tries to radiate or diffuse heat. So, they try to make the nearby vicinity area, they try to make from either they solidify them or entire earth crust which is available in the rock form, they try to heat them. Other way is that if there are some water which is deep inside the earth crust, they try to become hot and hot. So, they form a steam which tries to come out from the earth crust. So, through this there has to be some passage that this steam has to come out, but since there is no passage, but over the years there are different cracks are developed due to the earthquake or any other geographical accident. Through this process there are vents or cracks that are developed through which these materials tries to come out. So, basically we have one region which is called as magma, second region is called as igneous rock, because these are like volume of crust which are available. So, we call this as a igneous rock, which is nothing but your hot rock. Then third category is in the region C. So, region C is like a reservoir, permeable reservoir. So, basically it is a permeable water reservoir. So, whatever water that comes, when they come out from this earth crust, they tries to store in this particular belt which we call as a permeable reservoir. But this permeable reservoir is also capped in another area, and that is called as solid rock. So, basically B is called as igneous rock, that is a fire rock, and D is nothing but heat rock or a solid rock that is also hot. And now, all these earth materials when they try to come out, they either come out in the form of, so E is nothing but your, we can say it is a passage or vents, and in geothermal category we call as fisheries. So, they are nothing but the passages. Now, through these passages, when the inside earth material they try to come, we land off seeing in the net effect as hot springs or hot well, and also we have hot well, hot spring, and also in the form of geysers. Geyser means it is a supply of hot water. So, all these things we see in the earth surface. So, essentially these are the areas we see the effect of underground earth crust on the surface. But however, if you look at actually these geothermal systems, we can categorize the type of heat which they contain in two ways. One is called as magmatic steam, which originates from the magma. Other is meteoritic steam, which originates from the groundwater heated by magma. So, magma, some materials that comes directly through some passage. So, it is like a hot spring, or we can say it is a directly it can come. Other things, earth crust that comes through these fisheries passages. So, there are two ways, either to harness this geothermal energy. So, what you do from the earth surface, you go underground, try to reach hot rock or this fire rock, and put your fluid from the outside or from the ground, and then try to heat up that fluid. That means, to go into this we need to go towards maybe 32 kilometer deep to arrive at this zone B. That is one way. Other way is that in case you do not go deep into these regions, let us say this deep is around 32 kilometer. If you are unable to go that, then what we are in the regions, let us say in the region D, where we can have impermeable hot rock, or in the region C we can reach in the form of permeable, porous permeable reservoir, where we can extract these fluids, because they are actually reservoir heat source which are available, and we can extract these fluids to the ground and again re-inject. So, that is what essentially the entire geothermal system does. So, through this process we classify different types of geothermal resources. One is hydrothermal systems, second geopressurized systems, third is petrothermal systems. So, in the geothermal systems we mainly target either target the liquid regions. So, either it can be liquid, we can tap the fluid which is inside the earth crust, either in the they are completely high temperature liquids or they can be high temperature vapors. So, of course, pressure is much higher. So, they are stored in that regions. So, that is what we call this as a hydrothermal systems. That means, we are extracting the fluid from the earth crust. Other category of systems is geopressurized systems, in which we tap water from the underground aquifer. So, basically we are going to that water reservoir, that is zone C, which was shown in that things. So, there we have this permeable rock, gravels, sand. So, when you go close to 2.5 kilometer to 9 kilometer depth, we reach this particular point. So, where the energies are available in pressurized form with a what we say in a through rock, gravels or sand. So, we plan to tap them. So, geopressurized thought to be a temperature of 160 degree centigrades, pressure can be 1000 bar, 1000 bar is too high. So, that but with high salinity. High salinity means it is a very saline water, and of course, it is saturated with natural gas, which is mainly methane, and often we call this water as brine, because it is not in its purest form, it is in the form water is there, and that water can be either liquid dominated or vapor dominated, and in which they are diffused with natural gas. So, considering all of them, we say we call this as a brine. Then third category is the petrothermal systems. They make use of hot dry rock, for which the temperature is available in the range of 150 to 300 degree centigrade with close proximity, and of course, these contribute 85% of geothermal resource of any type. And these rocks are also available in moderate depth, but they are highly impermeable. So, in order to extract this energy, we require a carrier fluid which has to be injected or pumped into the ground. So, basically petrothermal systems uses outside fluid which is pumped into those rock regions and try to harness the energy. And hydrothermal systems is the other side of story, where we do not re-inject any fluid outside, rather we take out the inside fluid to the ground, make use of it and then re-inject it. So, in our discussions we will mostly focus on the hydrothermal systems, that makes some similarity with our steam power plant, in which we have discussed about the thermodynamic cycles that can be useful for this course. So, in our discussions we will try to focus on only on hydrothermal systems. They are of two types, one is vapor dominated geothermal systems, other is liquid dominated geothermal systems. So, first we will discuss about this vapor dominated geothermal systems. So, you refer to this thermodynamic circuits. What this circuit represents here is a vapor dominated hydrothermal systems. We can say we have digged a well. Well is nothing but we can dig a well on the earth surface, keep entering into the earth crust, and through this dig well we extract the fluid, and this fluid is nothing but typically we have this brine. And when you take out this fluid, and there is a valve which is there is a throttle valve which of course regulates the pressure, and of course you have the centrifugal separator. So, in the centrifugal separator what does this do is that it takes all unwanted products, all unwanted corrosive products from this brine, and whatever it goes to the turbine, ideally vapor has to expand in the turbine. So, ideally it goes whatever purest form which is available as a water. So, we say whatever goes into the turbine is nothing but water vapor, and rest of the things are gets discharged outside, and rest of the things are similar to a Rankine cycle, where after turbine's expansion it goes to the condenser. Through this condenser, that is a heat rejection systems. So, heat rejection system means that we have a cooling tower that supplies the feed water systems to this condenser. So, since it is also water and this is also vapor, so you can have a direct contact type condenser, then condensate pump, and whatever left out things, that means whatever left out water, they again re-injected through this well. So, this is this. So, through well we extract, purify, use it, and then we dump into the well again. So, this is how this thermal circuit works. Now, if you understand this diagram, if you represent this in a temperature entropy diagrams, now with a relative comparison, we say we do not have a boiler or steam generator as we see in a Rankine cycle. So, we start with locations where already steam is available to us. So, that means we are available at some particular point, that is state point 1, but at state point 1 we cannot directly expand in the turbines. So, it has to go through the state 3. So, state 3 means through some separation process only vapor comes to the turbines. So, it tries to expand. So, when it expands, we have this isentropic process 3-4s. If it is a non-isentropic, it follows 3-4. Then rest of the things is condensation process, that is from 4 to 5. So, there is of course, there is no pump work, but even though there is a condensate pump, but pump work is very negligible as compared to this thing that is normally happens. And again the supply for the condenser or feed water system is achieved through 0.7. So, that is nothing but the 0.7 is the cooling tower exit, and that supply necessary water to this cooling medium. So, this is about the operations. So, we will try to put some numbers, because those numbers your working fluid is available. So, one thing is that water in vaporized form into steam, it reaches to the surface almost as close to up, these are the temperature which availability of temperature, that is we have 205 degree centigrade and 8 bar pressures. And if you can tap those kind of working fluid, then only that will be suitable for turboelectric power plants. So, here these processes I have already explained, like the water that comes in a saturated conditions, they are at 35 bar and 200 degree centigrade. There is a drop in pressure through this drop in process, and that 1-2 process is throttling. Again this drop in process gives slightly superheat conditions. So, we reach, so initially when it comes at higher pressure, but at saturated conditions, but when it actually enters into the turbine, pressure drops, there is a drop in pressure, but we reach in a superheated conditions, and that we expand in the turbine. So, this is what we achieve for a vapor dominated systems. So, other part of things that is more important, that the mass flow rate reinjections is of course less than the originating well, because there are losses in the centrifugal system, steam jet rejector, evaporation, drift and blow down. So, whatever mass of water that is available in the form of brine, so the content of water gets reduced when it is reinjected. Of course, that is quite obvious. Now, there are another category of geothermal systems in which the system is liquid dominated. So, liquid dominated, like if you refer our previous figure, we started the expansion in the turbine when the water availability or brine availability is already in the saturated vapor. So, this is nothing but saturated vapor, and this side we have saturated liquid line. So, here in a vapor dominated systems, the availability of your working fluid is already in the saturated vapor line. But if you look at the liquid dominated systems, the availability of working fluid is not at saturated vapor line, rather it is close to saturated liquid line. So, That is the essential difference in a liquid dominated systems and vapor dominated systems. So, then what happens? Then we have to use, there are two types of methods that we use. Either we use the same working fluid and make it vapor and then use in the turbine. Other way is that instead of taking that as working fluid, which is not at all suitable for expansion, we normally use a binary systems or binary cycle systems. So, in a binary cycle systems, what we normally do is that we use the underground energy available in the brine as a heat source, and that heat source is being used to vaporize our secondary working fluid. Since we have using a secondary working fluid, that cycle we call this as a binary cycles. So, normally what is the main demerit in the liquid dominated systems? Because when water comes from underground in the form of brine, there are various degrees of salinity and they range from 3000 to 2,80,000 ppm dissolved solids. So, separation is a big task. So, that is the reason a separator system, what we call as flash separator, is normally used. So, we call this as a flash based systems. But the advantage we have is that when you look at liquid dominated systems, the underground temperatures which are available to us is closely in the range of 175 to 315 degrees centigrades, and of course, they are at high pressure and we take them for our use. Now, let us try to understand something basic difference what we get in a flash steam systems and it is a liquid dominated. So, we see that from the underground reservoir we get this brine and this brine enters into the flash separator, and this is the most critical part for a liquid dominated systems, because brine contains high salinity water. So, what we require now in a single flash systems, we need same working fluid will be used in our thermodynamic cycle, which is supposed to be fed to the turbine. So, for that reasons, whatever water or brine is available, which is in the saturated liquid form, that is state 1, and through this when you take out this brine, there is a drop in pressure. So, first pressure drop takes place from 1 to 2. Now, from 2 to 3 there is a flash separator. So, basically that separator does the water part, whatever vapor contents in this brine, they take it out, and liquid part that sends it back. So, that is the job of this flash separator. So, at point 3, which is somewhere in the region liquid vapor region. So, this is saturated liquid, this is saturated vapor and this is liquid vapor regions. So, initially we have this brine that comes. So, and this side we say only water vapor. So, that means after these separations, water vapor we take out and it goes to state 4, that is the inlet condition for the turbine, where it expands to 0.6, then it goes to condenser, and here also since working fluid is same, we can use the direct contact type of condensers, and rest of the cycle is simple. And whatever again at point 3, we say what is this unused brine that comes out, again re-injected into the well. So, this is how single flashed steam based systems, and it is a liquid dominated geothermal system. Now, in a binary cycle what we do? So, we have the same brine, but we do not use the same brine in the working fluid. And if you look at, there are two parts, one is the brine that comes from the underground reservoir, and through this appropriate throttling it enters to a heat exchanger. So, through this heat exchanger the brine releases heat to the secondary fluid. So, this secondary fluid constitutes the working fluid for our thermal cycles. So, those working fluids are organic fluids, and they are mainly isobutane, and they are mainly low boiling point fluids, typically isobutane, freon, for which their boiling point is minus 10 degree centigrades, and for freon 12 it is minus 29.8 degree centigrades, and through these fluids we can operate them at relatively high pressure corresponding to source water and heat sink temperatures. So, a liquid dominated systems use a secondary fluid, and we call this as a binary cycle. Other parts are almost similar, because it also follows the conventional Rankine cycle for these power generation systems. So, this is all about the lecture contents that I am supposed to discuss. Now, based on our discussions, we will try to solve some numerical problems. So, these numerical problems what we have is something similar to what we solved in a Rankine cycle systems, where we have superheated steam, saturated steam, but only difference between them is that we try to bypass at least what happens in the boiler or steam generators. So, basically speaking, we have already available steam which is available either in the saturated liquid line or saturated vapor line. So, your primary we have to use the same steam tables or temperature entropy diagrams for water systems. So, the first problem, let us try to understand that it is a vapor dominated geothermal systems, and with a capacity of 100 megawatt. Saturated steam is extracted from the oil with a shut-off pressure at 30 bar. Since it is a saturated steam, obviously the state point 1 in this thermal circuit lies on the saturated vapor line, and this is liquid plus vapor. If you refer these TS diagrams, so it is a critical point. This side is saturated vapor line, this line is saturated liquid line, and in between it is liquid plus vapor line. So, we locate the point, that point 1 is at 30 bar. Steam enters the turbine at 7 bar and condenses up to 0.2 bar, but steam enters the turbine at 7 bar. So, 0.3 that is at 7 bar, but this pressure is available at let us say 30 bar. So, 1 to 2 and further 3, it is a throttling process that is already defined, in which enthalpy remains same, and from 3 to 4, 4s is a expansion in turbines. So, we have given with an isentropic efficiency of 0.8. Then we have this combined efficiency of turbine generator, that is 0.9, that means turbine plus generator, they have this combined efficiency of 0.9. So, essentially effectively it is whatever power developed by the turbine, 90% of them is converted to electricity. Then other information that is available for this side, that is feed water systems or cooling through this cooling tower. So, we have this cooling tower conditions which is at 22 degrees centigrades, and re-injection occurs prior to cooling tower. Okay. So, this is the problem, and whatever we have asked, we are essentially asked to find the steam flow rate in the turbine, cooling water flow rate in the condenser, then heat rate and efficiency of the systems. Heat rate means how much heat we are actually tapping from this brine. So, let us try to understand the problem. For this problem, you have to refer steam table. So, again we have to relook into the steam table with the given data available to us. So, first thing let us say what is state 1. So, state 1 is at P1, that is 30 bar, and that point 1 is saturated. So, at these conditions saturated pressure table can be referred, and we can write H1 is equal to that is enthalpy is nothing but saturated vapor region, that is at 30 bar. So, from this steam table this number is 2804.2 kilojoule per kg. Then we have state 3. State 3 means inlet to turbine, and we in between of course we have this throttle valve, but again there is initial drop in pressure, and maybe we can directly say from 1 to 3 is as we can refer it as constant enthalpy process. So, when you say constant enthalpy process, so we can use this H1 data to calculate the enthalpy at state 3, and enthalpy at state 3 is nothing but slightly superheated region. So, we can note down here, and H3, and that is at is equal to 2804.2 kilojoule per kg. So, we have two data here, and point 3 is like P 3, at that point it is pressure is 7 bar. So, there are two data, pressure and enthalpy. So, this will give you this saturated temperature T 3 as 180 degree centigrades. To have this number we have to refer superheated table, for which two data is required, H 3 and P 3, and we get T 3 is this. Okay. And for this pressure, if you take saturated temperature at 7 bar, so this number is 165 degree centigrades. So, we can say degree of superheat that means this drop in pressure gives rise to a degree of superheat is about 15 degree centigrades, that is difference between these two. Now, we are already in the state 3, then we will look into the expansion process in the turbine. Then we have to see for state 4 and 4s. So, process is isentropic, and but that where P 4s and P 4, that pressure is 0.2 bar, right, and process is isentropic, which means S 3 is equal to S 4s, and S 4s is nothing but SF plus X 4s into Sg minus SF, and this value has to be calculated at 0.2 bar. So, the data will give you what is that your Sg is equal to 7.9085 kilojoule per kg Kelvin. So, this will have, for this you have to use saturated table for pressure, and SF we have 0.832 kilojoule per kg Kelvin. Already we have S 3. S 3 can be found out from the state 3 data, like from this conditions S 3 of 2804.2 kilojoule per kg S 3 and P 3 is 7 bar. So, this will imply S 3 is equal to 6.9656 kilojoule per kg Kelvin. So, from these equations we have S 3, we have SF, Sg, SF. So, this will give you X 4s is S 3 minus SF divided by Sg minus SF, and we arrive at this number as 0.866. So, at this point, so at the point 4s we calculate what is X 4s 0.866. So, once we know this, then we can find out H4S is equal to HF at state 4 plus X4S Sg minus HF. So, the conditions that we have is that at P4 is equal to 0.2 bar, if you take saturated table pressure data, so this will give you HFG is equal to 2358.3 kilojoule per kg, HF is equal to 251.4 kilojoule per kg. Now, from this data we can arrive at what is H4S, and that number it is 2293.7 kilojoule per kg. So, we have H4S, then we can calculate isentropic work. So, W isentropic work is equal to H3 minus H4S. This number is already we have H3 is 2804.2, H4S 2293.7. So, this is 510.5 kilojoule per kg. Then actual work. So, actual work stands as turbine work, that is isentropic efficiency of the turbine into W isentropic. So, this number is, if we multiply 0.8 into this number, so we get turbine work is 408.5 kilojoule per kg. Then, but you have the power generated 100 megawatt at an turbine generator unit combined efficiency of 0.9. So, we can say how much power transmitted. Which is, I am writing just as W is equal to WT into 0.9. So, this number is actually 367.56 kilojoule per kg. So, this is the power we should be working on to calculate the rest number of the questions. So, we also know power which is developed is 100 megawatt, and so we can now calculate what is the power which is we get per cycle is 367.56 kilojoule per kg. So, we can say steam production, how much steam is required is equal to 100 into 10 to the power 3 divided by how much power gets transmitted, that is 376.56. So, steam requirement or mass flow rate of steam is 272 kg per second. What is volume flow rate? So, volume flow rate of the steam is equal to mass into specific volume. So, V3. So, V3 into m dot St. So, V3 is calculated based on the state point 3, and that V3 is equal to V3, this number is we can get 4045 meter cube per kg. So, volume of the steam flow would be 1110 meter cube per second. So, volume flow rate is this, mass flow rate is this. So, this is what we required, what is the steam flow rate, or we can say what is the volume flow rate of the steam. So, that we get from this part. Now, we will move on to this condenser part. So, condenser cooling water part, we can write this equation plus cooling tower. We can use this equation, that is through at heat exchange process, m dot 7 into H 5 minus H 7 is equal to m dot 4 into, because this is this part and this is this part, and heat is rejected from this condenser. So, m dot 4 into H 4 minus H 5. So, we know that this cooling tower exit condition is 22 degree centigrade. So, condition 7 has to be found out from this data. So, at saturated temperature of 22 degree centigrade, this will imply, steam table data will imply H 7 is equal to 92.33 kilojoule per kg, and we also know already H 3 is 2804.2 kilojoule per kg. We also have W T is equal to H 3 minus H 4, turbine work is 408.4. So, this will give you what is the value of H 4 is 2395.8 kilojoule per kg. So, we have H 4, we have H 7, then what is not known, what is H 5. So, H 5 can be calculated because that is at turbine pressure, that is 0.2 bar, that is nothing but HF. H 5 is equal to HF to be calculated as 0.2 bar, and that is 251.4 kilojoule per kg. So, from these equations all the numbers are known, H 5, H 4, H 7. So, this will give you cooling water requirement is 3667 kg per second, and volume flow rate for the water would be 3.667 meter cube per second. Then next job is to find out heat added. So, heat added, so we started with 0.1, ended with 0.7. So, heat added, which is Q in per unit mass, is H 1 minus H 6. So, all these numbers are known. H 1 is 2804.2 minus 251.4. So, Q in is 2552.8 kilojoule per kg. Then we need to efficiency of the systems. So, efficiency of the system is W by Q in. So, W is already 367.54, that is the final work output, divided by 2552.8. So, efficiency of the plant becomes, or system becomes 0.15 or approximately 15%, or that is equal to 15%. So, efficiency is known. And next thing that is required is the heat rate. So, heat rate by definition we write HR is Q in into m dot steam into 3600 divided by efficiency into this power, that is in kilowatt, and this is normally represented as kilojoule per kilowatt hour. So, through this conversion we define these things. So, we have already data, what is Q in 2552.8, steam flow rate is 272 kg, it was kg per second. So, that is what we multiplied 3600 to bring it to kg per hour. Then efficiency is already calculated 0.15 into power is 100 megawatt. So, we have to make it kilowatt. So, 100 into 10 to the power 3. So, this is in kilojoule and this is in kilowatt hour. So, this unit now turns out to be kilojoule per kilowatt hour. So, we say HR heat rate is 156,231 kilojoule per kilowatt hour. So, this is about the big problem which is for vapor dominated systems. Now, we will look into a small problems in which we have to see it is a liquid dominated systems. So, the problem statement is for a liquid dominated geothermal systems. So, we started with same diagram, temperature entropy diagram. So, we have liquid here, we have vapor here, and what is the question that is given is that we have an instrument which is called as cyclone separator or flash separator, and that flash separator separates the brine that enters into the circuit, and that separation happens at point 3. So, the question was asked that geothermal system, the hot water reservoir, it contains water at 240 degree centigrade and 11 bar. So, your state 1 condition is nothing but your H1 is your HF at 240 degree centigrades. Since it is already in a saturated liquid regions, so here we have to use this temperature as benchmark. So, at this temperature what is the enthalpy we can calculate from the saturated temperature table. So, that number is 1037.53 kilojoule per kg. Again process 1 to 2 is constant enthalpy process, 1 to 2 to 3. So, which means H3 is equal to H1. So, H1 data is already there, but H3 data is not with us. So, H3 is at a pressure. So, this pressure is at 240 degree centigrade and 11 bar, and this pressure is 7 bar. So, H3 is equal to H1, that is nothing but HF plus X3 into HFG, and this pressure is at 7 bar. So, from this saturated table at 7 bar, which will imply HF is equal to 697.22 kilojoule per kg, and this HF is nothing but in this figure it is your H5, and Hg is equal to 2763.5 kilojoule per kg. Now, with respect to this figure, this point is H4, right. So, we have H1 is already here. So, this equation will give you X3 is equal to 1037.3 minus 697.22 and 2763.5 minus 697.22. So, ultimately we have X3 is equal to 0.16. So, the question was asked that we need two parts. One is what is the mass flow rate of water from the well and re-injected brine per unit mass flow rate into the turbines. So, m dot turbine flow rate is 1 unit, let us say 1 kg per second. Now, with these things we can say m dot W would be nothing but 1 by x3, and this number is 1 by 0.16. So, that is 6.2. So, per kg per second, per unit mass flow of the turbine, the mass flow rate from the well would be 6.2 kg per second. Then mass of the brine that is reinjected is, so that is 6.2 comes here, 1 unit it goes to turbine and rest of the things comes here. So, that is m dot b will be 6.2 minus 1 unit. So, this is 5.2 kg per second. Now, what is the enthalpy ratio? Enthalpy ratio of spent brine to the steam, that is Y is equal to spent brine is H5 divided by H4 into m dot b, because that is the amount that was spent per unit mass flow rate of water into the turbine. So, H5 and H4 number is known, that is 697.22 divided by H4 is 2763.5 into 5.2. So, Y is equal to 1.32. So, enthalpy ratio turns out to be 1.32. So, with this I conclude this geothermal sections in this lecture. Thank you for your attention.